Sunrise versus sunset, retinal adaptation, circadian effects, and perceptual differences. Both casual observers and scientists have noted that the visual experience of sunrise can feel notably different from sunset, even if the physics of sunlight scattering are symmetric. A key reason is how our visual system, eyes and brain, responds differently at dawn versus dusk. The phenomenon described as a retinal haze during rising or setting sun refers to the eye's adjustment period when transitioning between dark and light conditions. Below, we explore the neuroscience of these perception differences, including retinal adaptation and circadian physiology, as well as some macro-level factors. Retinal adaptation at dawn versus dusk. Light versus dark adaptation. The human eye does not adapt to increasing and decreasing light at the same rate. Dark adaptation, adjusting from bright light to darkness, is a slow process. It takes on the order of 20 to 30 minutes, or more, for rod photoreceptors to fully recover sensitivity after bright light exposure. In contrast, light adaptation, adjusting from darkness to bright light, is much faster, often achieving a new equilibrium within a few minutes or even seconds. This difference means that at sunset, going from bright day to darkness, our eyes lag behind the rapid fall in ambient light, whereas at sunrise, darkness to bright light, our eyes respond and reset very quickly to the new brightness. Sunset, in the evening, your eyes have been photopic, daylight, adapted and cannot increase sensitivity as fast as the sky is darkening. As dusk deepens, the rod cells gradually take over vision, entering the mesopic/scotopic range, but there is a delay before they reach peak sensitivity. This lag causes some colors and details to fade from perception during sunset. Certain hues may disappear or appear off because the cones are falling below their threshold before rods are fully ready to contribute. In other words, you start to lose color vision and acuity faster than your eye can compensate, producing a subtle hazy dimness in perception. Sunrise, before dawn, after a night in the dark, your eyes are dark adapted with highly sensitive rods and dilated pupils. As the first light appears, you notice every faint change in sky color because your visual system is maximally sensitive. Even minor brightening at dawn produces noticeable color shifts. Once the sun actually rises, however, the intense light rapidly bleaches the rod photopigment and dazzles the eyes, but within about 5 minutes your cones adapt and the glare subsides. This swift transition from rod-dominated night vision to cone-dominated day vision can feel abrupt and intense, as if a haze is suddenly lifting or morphing. The sunrise retinal haze thus stems from the retina scrambling to dim its sensitivity, to avoid overload, a dynamic process that is faster and more acute than the gradual sensitivity increase at sunset. Color perception and the Purkinje effect. Another aspect is the shift in color sensitivity under different light levels, the Purkinje effect. In very low light, rods drive vision and are most sensitive to blue-green wavelengths, while cones, which see color, are not active. At dusk, as illumination drops, we experience a blue shift in relative brightness. Reds become much darker relative to blues/greens. For example, a red flower that looked bright in daylight may appear nearly black in twilight, whereas green foliage or a blue object stays comparatively brighter. Figure 1 below illustrates this effect. During sunset, this means some warm colors fade out quickly, contributing to the peculiar dim haze of vision. During sunrise, the reverse happens. The world shifts from the rod's blue-tinted, color-starved view to the full color spectrum as cones kick in. Reds and other colors rapidly pop back into visibility as daylight grows. This rapid color transformation at dawn can make sunrise visually striking, as the scene literally gains colors that were imperceptible a few minutes earlier. Figure 1. Simulation of the Purkinje effect on a red flower and green leaves under different lighting. Top, photopic, bright daylight, the red petals are vivid against green. Middle, mesopic, twilight, colors desaturate and the red darkens. Bottom, scotopic, night, vision is monochromatic via rods. The red petals appear almost black while the foliage remains somewhat visible. This illustrates how color perception shifts toward blue-green sensitivity in low light, affecting sunrise and sunset views. Visual tricks in twilight. At sunset, observers often linger their gaze in certain ways to prolong night vision. For instance, stargazers use averted vision, looking slightly to the side, to detect faint stars in twilight using rod-rich peripheral retina. You might catch the first stars or planets in the darkening blue sky by not looking directly at them, effectively tricking your eyes into seeing dim points while part of the sky is still bright. Such techniques can extend one's perception of the darkening sky, maintaining that deep blue twilight a bit longer. In the morning, however, these tricks are short-lived. As soon as dawn light intensifies, the rod cells saturate and stop functioning, within minutes after sunrise, so stars and faint details vanish quickly. Even an experienced night observer can only hold on to dark-adapted vision for at most 20 to 30 minutes past sunrise. Beyond that, the encroaching daylight inevitably floods the retina, erasing the nighttime sensitivity. In summary, dusk offers a gentle fade-in of rod vision, whereas dawn forces a rapid fade-out of it, making the sunrise transition feel more abrupt and scientifically interesting in terms of retinal processing. Circadian rhythms and neural processing. Beyond immediate photoreceptor chemistry, our visual system's response at sunrise versus sunset is also shaped by circadian biology, daily rhythms in the eye and brain that anticipate light changes. The retina itself contains an internal clock that modulates its neurons and chemicals over the 24-hour cycle. This leads to asymmetries in how visual signals are handled in morning versus evening. Rod-cone interaction. At night, the retina boosts sensitivity by electrically coupling rod cells to cone cells. This means rod signals, detecting very dim light, can flow into the cone pathways, enhancing vision in near-dark conditions. The retinal clock achieves this by releasing melatonin in darkness, which suppresses dopamine. Low dopamine causes special gap junction channels between rods and cones to open. As a result, during dusk and night the retina is configured to pool rod inputs and maximize light detection. By dawn, this reverses. The approaching daylight triggers increased retinal dopamine release, melatonin levels drop at morning, which uncouples rods from cones by closing their gap junctions. In essence, the retina actively switches to a daytime mode, prioritizing visual acuity and color, cone function, over raw sensitivity. This circadian adjustment means the sunrise transition is sharpened, rod contributions are cut off around dawn, making the switch to cone vision more pronounced. At sunset, the opposite shift, cones yielding to rods, is more gradual because the retinal network is adding sensitivity, opening rod-cone links, to help you see as it gets dark. A scientist finds sunrise compelling because it showcases this coordinated neural switch, a brain/eye mechanism evolved to separate night and day vision very clearly. Alertness and perception. The timing of sunrise and sunset also ties into whole-body rhythms. Morning light has a strong influence on the suprachiasmatic nucleus, SCN, the brain's master clock, signaling that it's time to be awake. The intrinsically photosensitive retinal ganglion cells, iPRGCs, containing melanopsin respond robustly to the increasing light levels at dawn, suppressing the sleep hormone melatonin systemically and boosting cortisol and alertness for the day. This means at sunrise, your brain and eyes are primed to respond, your night vision is acute and your brain is gearing up to transition to daytime function. By contrast, at sunset the body is winding down, melatonin secretion begins with darkness, and fatigue from the day may set in. Indeed, researchers Lynch and Livingston note that by day's end our eyes may be fatigued, and as light fades we do not perceive all the nuances of color due to slower adaptation and perhaps reduced attention. At dawn, however, coming from darkness, our visual system is rested and highly sensitive, catching every minute color change in the sky. This neurochemical context adds to why sunrise visuals can seem crisper or more intense. Our neural circuitry is effectively more receptive in the morning, aiding survival by quickly entraining to daylight, whereas in the evening the same system is relaxing its vigilance. In summary, our biological clock creates an uneven playing field. Nighttime neural adaptations make dusk a smooth sensitivity ramp-up, while morning mechanisms enforce a swift handover to daylight vision. This makes the rising sun's retinal experience rich with rapid neural changes, a fact not lost on scientists studying vision. Macro-level optical factors, atmosphere and light. Aside from human physiology, there are external, atmospheric differences between sunrise and sunset that influence what we see. Physically, sunrise and sunset involve the same geometry of the sun's light passing through a long slice of the atmosphere, producing red/orange hues and twilight gradients. However, environmental conditions around dawn versus dusk are often different. Air clarity: overnight, the atmosphere tends to settle and cleanse. Winds calm down, and human activities, which produce smoke, dust, pollution, pause. By dawn, the air is usually at its clearest of the day. In contrast, by sunset the atmosphere has accumulated a day's worth of particulates and haze. Lynch and Livingston explain that at sunset the sky is often full of pollutants and windborne particles, whereas the dawn is clearer than any other time of day. Color vividness and spread: clear morning air allows purer wavelengths to come through. Thus, sunrise colors, the reds, pinks, golds near the horizon, can be extremely vibrant and saturated in a pristine sky. These colors are often concentrated around the rising sun, giving a tidy focal display of color. At sunset, the heavier aerosol load scatters light more widely across the sky dome, sometimes producing a broader swath of orange or purple afterglow, but those colors may appear diluted or washed out compared to sunrise. Some observers describe sunsets as more chaotic in coloration, versus the often cleaner, well-defined gradients of sunrise. Which one looks prettier can be subjective, but scientifically you can often tell a photo of sunrise from sunset by these characteristics: sunset being a bit more diffuse and reddish-yellow overall, sunrise having bolder contrasts against a darker sky. Twilight duration: the length of twilight, the blue hour and dawn/dusk glow, is the same in reverse for sunrise and sunset under the same conditions. However, as mentioned, our perception of that duration can differ. In the evening, twilight might feel shorter in terms of visible detail because our eyes struggle to keep up with darkening, losing detail early. In the morning, twilight might feel drawn out in terms of color observation because we start in darkness and can detect even faint pre-dawn light. Moreover, fewer people are awake and outside during pre-dawn twilight, so the sunrise haze phenomena are less frequently witnessed, adding to their intrigue. Conclusion: in essence, a rising sun's retinal haze, the visual experience as your eyes adjust to dawn, is more dynamic and complex than its sunset counterpart due to a combination of factors. On the sensory level, your retina and brain are transitioning from a sensitized night mode to a high-acuity day mode, a rapid flip marked by quick light adaptation, rod/cone role reversal, and circadian neurochemistry, retinal dopamine, melatonin, etc., geared to daytime, all of which make dawn's visual changes especially pronounced. At sunset, the change is slower and in the opposite direction. The eye's adaptation lags behind the fading light, and the visual system gradually relaxes into night mode, causing a gentler, less noticeable fade. Colors quietly disappear as darkness comes. From the observer's perspective, this means dawn offers a richer palette of perceived colors and rapid changes. The sky's hues seem to blossom out of blackness, whereas dusk is a more subtle dimming of an already lit world. And on a macro scale, a cleaner morning atmosphere often delivers crisper, more concentrated dawn colors, while the day's end leaves more haze for the sunset, affecting how dramatic each can appear. Both sunrise and sunset are beautiful physical events, but the neuroscience of vision makes their retinal hazes feel different. A scientist finds sunrise especially interesting because it encapsulates a high-speed interplay of photoreceptors and neural circuits resetting for a new day, as well as an extreme test of the eye's dynamic range. The naked eye observer, even without knowing the biology, unconsciously senses that something is different at dawn. The colors seem a bit more vivid, the experience a bit more intense. In sum, the rising sun's retinal haze is more interesting in the sense that your visual system is doing more complex work at that time, creating a unique and fleeting spectacle at the boundary of night and day. Sources: Lynch, D.K. and Livingston, W. 2001. Color and Light in Nature. Excerpt via Live Science on Human Perception Differences at Dawn.